Hello, everybody, and once again, a very warm welcome from Physics for Students, and a good evening to everyone. We are inviting you all to another exciting episode of our podcast, and we have today a remarkable young person, a remarkable guest with us, Abhinaba Upadhyay. I would consider him to be a rising name in the world of theoretical physics, currently working as an experimental research and a PhD student at the famous CERN, which requires no further mention. From the impactful publications in theoretical physics, Abhinav has got his hands on involvement in LHC simulations. His journey has been nothing short of fascinating. As a doctoral fellow at Athvash Lorand University, he is deeply engaged with detector control system for the CODEX B experiment, pushing the frontiers of dark sector searches. His work also extends to long-lived particle, or the LLP, decays at the muon stations of the LHCb detector, where he has contributed by designing HLT1 algorithms to perform real-time analysis. In today's discussion, we will explore the significant search for the CODEX B experiment, the dark matter, the researches, and most importantly, how we can make a career in CERN as a student or as those who are trying to follow. Without further ado, let me warmly welcome Abhinav. Abhinav, a warm welcome to our podcast from
Thank
Physics
you,
for
thank
Students.
you, thank you, Shanak. How
Yeah,
are you doing?
I am absolutely fine. If you can say hello to our subscribers, that would be great.
Hello, everyone.
Yeah, so
It's
we have
it's
got
it's really nice. Yeah. Hi,
Raghav already telling hello, sir. Okay. So, Abhinav,
hi, Raghav.
I think let us start with understanding CERN and LHC a little bit with your presentation, and then I would ask the viewers who are already there, they can ask questions related to CERN, LHC, and career development. So, you can put on the uh, presentation, and I will start from there.
Okay. Yeah. So, uh, I mean, these are some of the very famous photos at CERN. So here I'm standing beneath the Nataraja statue, which was a gift by Department of Atomic Energy, Government of India to CERN. Since 2017, India, we are lucky that India is an associate member state of CERN. And uh, as you all might know, CERN is located in the Swiss-French border, and the blue ring, which is LHC, it's spread across the two countries. Although the headquarters is of CERN is in Geneva, most of the offices are over there, and across this ring, which is the largest machine ever built by the mankind, exists, which is the Large Hadron Collider. And also, CERN is the birthplace of the World Wide Web. I mean, the loads of data that we collect here at CERN, in order to gain access to those data from scientists all across the world. Uh, Steve Bernard-Lee, in he it was part of his PhD thesis, if I am not wrong. He invented the World Wide Web here, right here at CERN. So that's a short introduction. But CERN currently has 24 member states and 10 associate member states. So I mean, we have participation from close to 70 uh, countries. And as you all might know, that at CERN there are four major experiments, and which uses the LHC, but there are experiments much more than those four big experiments. This is a geospatial view of the LHC and the four experiments, which are namely CMS, Alice, Atlas, and LHCb, as you might see where I'm pointing my cursor. So that's a brief introduction of CERN, and I'm happy to have any questions that you have about any introductory questions about CERN. Shonak?
Yes, I
Yeah.
think right at this moment they don't have any questions, so you
Okay.
can go ahead. Yeah.
So at CERN, uh, I mean, it's true that I mean we do physics studies at CERN, but does CERN only hire physicists? But I would say this is kind of a myth. I mean, the smallest department at CERN is the theoretical physics department, and most of the people here, like me, who work in experimental physics or in detector electronics, or there are IT people and there are software guys who relentlessly work day and night to make this big experiment work 24/7. And as I said that, I mean, there are there are some myths around CERN, that do we create Big Bang at CERN? I would like to clarify that no, currently we don't have that much energy to create the Big Bang, but we are close and we create a very baby universe, which is just 10 to the power minus 6 seconds after the Big Bang. So that's I mean, that's appreciable as well, I think. And
Abhinav, if I may
yeah,
interrupt, we have a
yes,
question coming in. If I can, with your permission, remove the slide
sure,
and take the question.
absolutely.
Yeah. Now, it's personal is asking, I got admission for Heidelberg University for my master's, and I will be focusing on particle physics. I would love to do internship at CERN as well. Any guidance for fresh master student?
First of all, congrats for your admission at the prestigious Heidelberg University. So in your masters, I think you can apply in two modes. One is you can apply for a technical studentship, or next year during January you can also apply for the CERN summer interns. Those are pretty good as well. They take 150 students, I think, all over the world. So you might have a chance over there, or you might talk with your supervisor at Heidelberg University and try to find a technical studentship at CERN for a year. And I think these are the two ways in which you can be at CERN.
Right, thanks. So you got the answer. We will go back to where Abhinav was talking about. Yeah.
Yeah. So so when these things are built, so there are always you have to take care of the people who are living. I mean, these are places of residence for people who are not scientists, and they have questions like, are we prone to radiations? To answer this, although we work with nuclear physics or advanced nuclear physics, but people living on the surface of Geneva are not prone to radiations. I'm just trying to answer some myths about CERN, because the entire facility is 100-meter underground, so it's pretty safe. And there has been there has been a secret ritual at CERN in front of the Nataraja statue. If you can see this photo over here, so it was a prank. It got really popular after the Higgs boson. Once the Higgs boson was popular, and now this became popular about CERN. But this was a parody done by some scientists, and we hope that this kind of parody doesn't happen again. And this photo is the photo of the first computer that hosted the first website in the world. This was at CERN. Um yeah, so this is pretty much about how CERN operates and what CERN is.
Right. So, so can we remove this slide, or you have
Yeah,
something more
yeah,
to
sure,
say? Okay.
sure, sure,
Okay.
sure.
So my question, I've got a question from Somnath, but can you tell that why was this Nataraj statue has been put up? I mean to say, any specific reason for that?
Yeah. So, I mean, there is a lot of funding flowing from every country to become a member state or an associate member state. If an India became an associate member of CERN in 2017, I think, and so it was a token of gift from the government of India to CERN. Uh, it's a token of honor.
Right, absolutely, absolutely. Okay, we have one question, but I don't know, Abhinav, is it related to the discussion today? Now, Somnath Safi is asking, hi, I am in job but want to pursue MSc in Astrophysics part time. Can you suggest any domestic or international institute?
I mean, domestically, you have Indian Institute of Astrophysics in India, as well as I think
I
IIST is
can,
there. But
yeah, I can
yeah,
suggest one
hmm.
thing, which I am in association, Professor Abhinab Datta, being
IIT
into the head
Indore.
of the department, yes, IIT Indore. So I can tell Somnath, if you want, I can even pass on his email ID to you. You can contact Abhirup sir. He is in the astrophysics department, and this is the right university which provides MSc in astrophysics. So I think that would answer the question. Yeah. Right. So, Abhinav, before we go into technical questions, I think me and as well as the viewers today watching right now would be willing to know about your journey, starting from MSc in physics at Jalandhar, from there, from India, how you moved into CERN, if you can let us know, and what are the issues also that you really faced, so that we also enrich the viewers to know that if you really face these issues, these are the things which you can overcome with.
Mhm. Right. Thanks for asking. So I did my bachelor's in physics from Calcutta University, and then I did my master's from NIT Jalandhar, their physics department. Although I mean, my work over there was mostly on Monte Carlo simulations of the LHC and theoretical physics mostly. So. Uh, but my research focus was mainly in experimental physics for my doctoral studies, and these doctoral programs. I mean, there are two ways how you can do your PhD at CERN. One is that you work in a university, and the university pays you to work for CERN. That is how you become an LHC user. You travel to CERN on and off for your work related to the university at CERN. And the second option is you have your office directly at CERN. That is, CERN recruits you and you get affiliated to a university to just get your degree, because CERN doesn't provide any degrees. So I was an LHC user for a year at Wrocław University in Budapest, and so there was a funding opportunity at CERN. I applied. I mean, obviously there are a lot of competition here, but so I mean, luckily I got through. But what they really look for, because it's experimental particle physics, they really don't. They are not really much into theory. I mean, if you are good at maths, if you are good at theoretical particle physics, it doesn't matter over here, because the theories are very well designated over here, already done by theoreticians, and we just want to implement it and make the LHC run and the experiments run. So if you are good in computing, if you are good in programming, if you are good in AI, if you are good in electronics, these are the core skills that people at Sun look for while hiring. Yeah, so I think that might help.
Thank you for this information. So, if you can chart us the exact path after completing MSc, what is the way? Is there that you need to apply to some websites, or how do you get into it?
So traditionally, either you while you are doing your masters, you might or your BTech, you might get into CERN as a summer intern, and you make good contact with a potential supervisor at CERN. That's a possibility, and later on you talk with a supervisor, build a good rapport, and and he agrees that he wants to take you as a doctoral student directly at CERN. That could happen. Or you try to get a PhD position in a university, and through the university you try to go to CERN. So that's also very much possible.
Is there any cutoff marks or any kind of an area which comes as a challenge? I mean, so there are so many students who might be applying for CERN, but how did you get into it?
So not marks is what they look for. If you, I mean, the main thing is good skills in data analysis, machine learning, and the skills that they look for. So if you have a good profiling programming, you have some good projects in programming, you have done some programming projects related to high energy physics, That really helps actually.
Okay.
So
So
marks
after
is not a barrier. Yeah.
now it's not a barrier. So after completing MSc, what was the next step that you do? Did you had a plan in your mind that you would go to CERN, or it just came through the process of your learning? How did it happen?
So I applied to universities, and I liked the work at University University, and I mean, I was hoping that I get into there, and I got there luckily at the university. And so this is what I'm suggesting, that you apply for PhD after masters or after your BTech to a university which is in one of the CERN experiments, which is affiliated to CERN. So there are lots of universities affiliated to CERN. You just have to look for high energy physics in this country, and you might get the universities which are working with CERN. Um, and so through the university, you can get to CERN very easily.
Okay, so this Lorand Advash University at Budapest, this is associated with CERN.
Yes, yes, yes. Yeah.
Okay,
So
okay,
that's how I got introduced, and then I applied for the position at CERN. And after interviews, I got into CERN. Yeah.
okay. Asking you a very candid question. I hope you don't
Yeah.
take me wrong. Do CERN? I think they pay money to the PhD students.
Yeah, so if you are an LHC user, and you are and your office is in the university itself, so then the university pays you, not CERN. But if you have your office at CERN, if you are a CERN doctoral student like me, then you are directly recruited by CERN. So obviously CERN pays you then, and the university is just there to give you the degree at the end of 3 or 4 years. Yeah.
Okay, thank you very much. Okay, we have got a question from its personnel. Can you please explain what are symmetry violation experiments going at CERN?
Right. So the most symmetry violation experiment, the most important symmetry violation experiment going on at CERN is LHCb, which I am working in. LHCb stands for Large Hadron Collider Beauty Experiment. So LHCb was technically built to work on the matter-antimatter symmetry. That's one of the prominent goals of LHCb, and they do it by studying uh, decays of heavy particles into particles that have beauty quarks in it. So that's what this big experiment does at CERN.
Okay, so it's personal. You got your answer. So taking it for further, Abhinav, when we go into CERN and we you work specifically on this CODEX B, what we experiment. Can you just let us know what exactly is CODEX B in a simplified manner?
Absolutely, I think I have some good slides for that. um, yeah, thank you. Yeah, so as we know that, I think that if people are interested in dark sectors, so they prominently know that most what what you see is not dark sector, it's the luminous matter. But for dark sector, 95% of the mass energy is dark energy plus dark matter, and we do not know how to detect them because they neither interact with any electromagnetic radiations, nor they interact with light, because light is an EM radiation, right? So, sorry, not this one. Yes. So let me introduce you to CODEX B, which is supposedly a future experiment. CODEX B is to be developed and installed in 2030. Currently, the CODEX B collaboration is working on CODEX Beta, which is the proponent version of CODEX B. So, in order to access funding for CODEX B, you need to do some proponent detector, a small detector, and prove that it's worthy of gaining the funding. So uh, what we do is that there are 2 points that you need to fix in the criteria to be a dark matter experiment. One is that since dark matter is not part of the standard model of particle physics, you have to filter it from all standard model signatures. So one is filtering, vetoing the experiment from all standard model signatures, and second is you have to make the detector components, the electronics, much more sensitive, because detecting dark matter requires is very sensitive on the electronics part. So in the so on your on your left, if you can see, the major LHC detectors like Atlas, CMS, LHCb, they are forward detectors. So for example, if this is the LHC beam, the LHCb detector is like this, it's placed like this. So from both sides the particle beams come and they collide, and perpendicular to this particle beam, particular perpendicular to the LHC ring, is CODEX B. So that is why we say that CODEX B is a transverse LLP detector. The LLP being a strong candidate for dark matter, you can see over here, this is the LHCb. If you see the um, right image, which is the right below image, this is the LHCb detector, and transverse to it is the cortex. This red region is for cortex P. So cortex P is a transverse LLP detector that searches for LLP in a direction transverse to the LHC beam. That would be a good introduction to cortex P, I think.
Fine. So we can remove this part, right? The
Yes,
slide for
yes.
the, okay. So what actually, when we talk of codex B, okay, we, we have another quick question coming up. Okay. So he's asking that how do we know on which side or orientation we need to place the detector?
Ah, so this is to answer this. I would try to answer this in a very generic way, because when you are, I mean, Codex P costs close to $10 million, and it's a lot of money. So, as experimental particle physicists, what we do is that we do not leave scope for anything. So, we don't know where, in which orientation it should be, but there are two orientations available, right? One is forward along the LHC beam, and one is perpendicular to it. So we try to cover as much phase space as we can, as much orientations as we can cover, the better will be our scope of detecting dark matter. So we don't leave scope for anything. That's how we work. That's how the experiments work.
Thank you, thank you, thank you very much. Coming to another question, Abhinav, we all know about CERN. I mean to say, we all those people who are working, and it is some kind of a very idealized picture where people really want to work. But if you can explain us that what is the primary mission of CERN, and how has its role evolved since the establishment?
So primarily CERN is a particle physics laboratory, but nowadays all the machine learning algorithms or the electronics and even the detector technology that we are using are being applied in medical physics. Or CERN has evolved to be a very general purpose research institute nowadays, because now we are working on quantum information, we are working in medical physics, we are working in climate. There is an experiment called the cloud experiment at CERN, which works on climate, on some climate studies. Pretty cool stuff. You can search it out on CERN's website. And there are other experiments related to seismology as well. And so CERN is like applying all the machineries that we are developing for the LHC, because LHC is a very unique machine itself, and to access any data from that you need some novel machine learning techniques which have never been built. I mean, the we closely have 500 petabytes of data at the end of each run at CERN. So in LHCb particular experiment, we have 1 terabyte data per second being stored, and to handle these, you need some novel machine learning algorithms and some lot of data facilities. So what we try to do is, we apart from the physics outcomes, we try to indulge this in medical physics and the all other branches, and make a good social impact out of those. That is what CERN's goal is nowadays.
Okay, that's wonderful. I mean, the one question which keeps me thinking is that the when the particles are, accelerated at such a high speed, I mean, it's almost close to 9.9999% to the speed of light, and when they're collided, uh, I know it would be very difficult right at this moment to answer as such, but these acceleration speed, what is the technology? I mean to say, how does it go so close and so much collisions within a few seconds? How does it happen?
Yeah. So in LHC, what we call is bunch crossing. So so what we do is that instead of shooting, because one thing, Shonak, it's very difficult to understand, is that if you shoot one proton from this direction and another proton from this direction, how will you make sure that these two will collide? These are so small, you can't control this on a microscopic level. So what we do is that we don't control. We use statistics. We, instead of throwing one proton and one proton from this side, we throw 1 billion and 1 billion of protons from both sides. And out of these 2 billion protons, in LHCb particularly, we are able to make 6 proton-proton collisions at any particular point of time. So so this is it regarding the collision point of view. But what you ask is that how are they able to accelerate this? So there are one thing that I know is that there are superconducting magnets for that to accelerate those, and you know there's no friction. I think mostly it's vacuum, but I think this is more this is more on the accelerator point of view. I work particularly in the detector departments at CERN, but in the accelerator departments, when I have talked with people, what I have understood is that superconducting magnets is a very crucial part of the acceleration. And there is another thing, which is another technique which is being used, is called plasma wake field acceleration as well. It's like, in a very layman term, it would be, suppose there is a ball which is your particle, and you are shooting a gun, you are shooting a bullet onto the ball, and hence you are adding momentum to the ball. So the plasma wake field is like a bullet which is adding momentum to the particles, and hence increasing the velocity more and more with time.
So we need that huge space. I mean to say that space is required. Why it is required? Is it that it has to travel to that time? I mean to say that huge space, the tunnel underway, this space is required for what is the reason that it should be going around that circumference?
So you don't, I mean, why do you need 27 kilometers is your question, right? So we don't actually, there was LEP, um, that is the predecessor of LHC, I think, yes. And that was smaller than the LHC. And there are other hadron colliders across the world which is smaller than LHC, much smaller than LHC. Those are, but the requirement. So when Peter Higgs gave the concept of Higgs boson, and people were too intrigued that if we can detect these and these, and it was very difficult to particularly detect Higgs because of its heavy mass. So massive particles are always difficult to detect because they occur at very high energy collisions. So the larger the ring, it's like the larger the ring, the higher is the chances of detecting more heavier particles. And particularly in the BSM point of view, which is beyond standard model point of view, we always want higher and higher energies. Yeah, so I think, why just LHC? Why not build bigger?
Absolutely. So that means all the experimentation and the huge innovation in terms of the machineries, these are now being used, I mean to say, for different purposes so that it benefits the society.
Yeah, they use these techniques being developed for particle physics for other applications. Yeah,
Right, absolutely. Abhinav, if you can tell me this question I have got, that what are
yeah.
the experimental signatures of particularly quark gluon plasma formation? I mean to say in heavy ion collisions, what are the experimental signatures that come up and how do they compare to theoretical predictions?
Right. So there are prominently three kind of collisions at LHC. One is proton-proton, then is proton-lead collision or any other ion maybe, or and there is the third kind which is lead-lead collision or gold-gold collisions, or that is your heavy ion collisions. So at LHC we have Alice, which is a dedicated experiment for heavy ion collisions. But nowadays, even Atlas, I'm not sure, but LHCb is working on heavy ion collisions as well, because it has a very different rapidity. It has a very unique rapidity uh, compared to uh, compared to Alice, Atlas, and Siemens. So rapidity, if I would quickly introduce you to the word rapidity, it is, so if this is your detector, so if this is your what do you say, if this is your LHC beam pipe and this is your detector, and particles are colliding across this way, then what happens is that two cones of scattered particles move from here, accelerate from here into the detector. So the angle at which you position the detector so that you have maximum exposure to the scattered debris from the collision is what makes your detector um, more prone to detecting things that you want to see, or more prone to collecting huge amounts of data. So in the context of this question which you asked is that we have things like what do you call this, jet quenching. Then there is called strangeness enhancement is something which we look for. These are pretty well established concepts, but a very interesting thing which I found out recently is that what Alice did is that they are looking for suppression in the production of charmonium pairs, which is a C antibar pair of charm quarks. So these are produced in suppression because I have a good slide for this actually. Shaunak, if you could share. Yeah, thank you. Uh, I think this one. Yeah, this one. If you would see that the C quark pairs which are formed, that is charmonium, these are not being able to form in the quark gluon plasma phase because of the interference of quarks and gluons which are freely moving. And that's why you want to look for, when you increase the temperature, I mean, of the LHC, I mean, when you have high energy collisions, you look for suppressed production of the charmonium state. So that's a very interesting point nowadays.
Thank you for this wonderful answer. The study of this quark gluon plasma, do they also contribute in our understanding of what is called quantum chromodynamics under certain extreme conditions?
Absolutely. So, for example, the example which I just now gave, the charmonium pair. So the C bar, they are coupled by strong interaction. I mean, by strong force, which is basically the theory of QCD. So QCD is also known as the theory of strong interaction, as you may know. Um, so if you can uh, better understand a signature for quark-gluon plasma formation, you can explore QCD at a very high energy. But understanding QCD just on the high energy side is not sometimes good enough. There is an experiment called gluonx experiment, um, gluex experiment. It's in the US, where they are also working on QCD in the low energy space. I mean, for low energy hadron collisions, and that's pretty relevant as well in the context of exploring QCD.
Right. Thank you. So I know maybe it is a myth. Are we producing miniature black holes or mini black holes which evaporates within a fraction of seconds at CERN? Are we trying to do, CERN is trying to do anything of that sort?
I mean, we can only answer this only when we are able to produce a big bang, right? We are not able to produce a big bang. What we are capturing, I mean, maybe a big bang is being produced, but what? No. So what we are able to capture, or what we're able to produce, is a universe which is 10 to the power minus 6 seconds after the big bang. So you can't, if you consider the big bang being a black hole, which I haven't delved much into this theory, but you are not, since you are not creating a big bang, so you can't say that you are creating black holes, right?
Thank you very much. Okay, we have another question from the same person coming up. That's good.
Ah,
Sir, I have one last question about finances. How can I make potential sources for earning while being in physics? It is hard to see from where to earn money for living. Important question,
I
I
mean, you
think.
can be a doctor. Yeah, Shanak, you were saying something.
You can go ahead with this. Yeah.
Yeah, so I think that if you are a technical student at CERN, you are paid very well, and I mean the salaries in Swiss are one of the highest in the world. So if you want to pursue a doctoral study here, or even a technical studentship here, it's worth it money wise. I think it's good to go.
Right. Thank you very much. Uh, we come to the next part of our discussion, which is about artificial intelligence, because AI is revolutionizing everything that we are seeing today. Coming later to the particle physics part, if you can tell us, Abhinav, that in in order to learn AI, especially for
Hmm.
particle
Hmm.
physics, what do we mean by learning AI? What are the things that we need to know, and how do we go about it?
Right. So, for example, if you want to learn AI, you don't start with generative AI, which the MBA guys or the finance guys studies nowadays. You want to learn AI, which is relevant to particle physics. So, the most important thing is that you need to learn simulations, which is quite good. And you can, mainly if you are in your masters or in your PhD, you can start with some basic machine learning course if it's available at your university. um, but applying it to high energy physics collision data would be much better, because we have huge amounts of data, and compared to any other scientific field, uh, you don't have the exposure of handling such amounts of data. So for example, um, here what we do is that per day 1 petabytes of data is stored at CERN. So if you want to handle such huge amounts of data, you need to consider whether you want to learn it from a professor who is working in high energy physics, or just take a random machine learning course online. So it's your call.
Absolutely. So, taking your answer, when we are talking of this huge amount of data, what is the technology that CERN uses in terms of storing the data? I'm sure there is
Uh,
no any kind of a hard disk or something which is a physical storage, but how does it do that?
Yeah, we have lots of hard disks, Sonam. But if you could just share my slides, I have a very interesting diagram for people. Yeah. So this is, suppose this is the LHCb detector, and uh, what we see, I mean, it's a huge detector. It's 5,600 tons. It's huge. So each sub part of this detector, so I have a close view of the detector, I think somewhere I have. Yeah, so this is the main detector, and each sub part, this rich vertex locator, ecal, hadronic calorimeter, muon stations, tracking stations, dipole magnet. They generate electronic data of their own from the collision which is happening here somewhere. So once each of the subdetectors create those electronic signals, those are combined and passed on to the trigger. Now here is the catch: the rate at which data is passed on to the trigger is 5 terabyte per second, but the rate at which we want to store data, or the capacity of data storage that we have at LHCb, is 1 terabyte per second. So you have to somehow filter out 4 terabyte of data per second, and that's what trigger does. Trigger is basically a set of machine learning algorithms which are fitted such that uh, can I please have the slides once? Yeah. So trigger is a set of machine learning algorithms which use the most novel techniques to filter out data which could be important for physics. Now, how can we understand that which kind of data is suitable for physics? Here is where simulation comes into play. So we have entire softwares written by physicists who which can replicate on a computer what the entire hardware detector can produce in a certain kind of collision. And from the particle simulations that we do using these Giant4, then there is Pythia, there is EventGen. These are different names to different softwares, and these softwares generate, and from there we learn that what kind of reaction a detector can give to a certain kind of a collision, and that is then fed into the machine learning algorithm which is the trigger, and it filters out data. And then there are much more, again, filtering out steps called reconstruction, stripping. These are a lot of technical terms, and it then finally passes on to the storage. This is the storage. There are huge data centers at CERN, and these store at the rate of 1 terabyte per second, or no, these store close to 100 gigabyte per second at LHCb, I would say. um, this is what the trigger does, and at a particular point of time the trigger uses close to 80,000 GPUs, 80,000 top of the line GPUs simultaneously working with the trigger to process this huge amount of data, because you have 1 second to process 5 terabytes. How will you process? You need simultaneous huge chains of GPUs. That's what we do. Yeah.
So we got two questions coming up from first from Somnath Safi, then from Raghav. So Somnath is asking, is the paper of experiment at CERN is easily available or we need membership?
So at CERN, we try to produce papers in open access journals. So I think that if it is from some collaboration like Atlas, CMS, LHCb, or Alice, you can find it in open access journals. So it will be available. You don't need membership for that. Yeah.
Okay, next question is from Raghav. He is asking that how a neutrino detector works.
Ah, cool. So it's a very generic question, Raghav, I would say, because for any kind of physics purpose, for example, if I talk of even a dark matter detector, there are several detectors across the world, and everyone has their own set of different detection techniques. So here what we so but there are two three primary criterias in dark matter detectors that we try to fit in for any kind of detector that we build. Similarly, for neutrino detection, we have one particular criteria that we want to fit in, that we want our detector to fit in, irrelevant of what technique it uses. It is that it needs to be shielded from the cosmic muons and the cosmic rays, and the different particles which are coming from the space. And so it has to be filtered from those, and that is why in many neutrino detectors, or even in dark matter detectors, they use thick walls of concrete to veto their detector from all these noises, as we say here, because something that we don't want is what we call noise in experimental physics.
Thank you. Very lucid understanding. I think, Raghav, you got your answer. Abhinav, my question to you next is that how do the observe, we try to observe, first my question would be that if you can tell us that what are the leading candidate particles for dark matter and how are current experiments designed to detect them? Okay, before that, we got a question. Let me first come to the subscribers' question, which is very important. Okay, Britastra is asking what is the meaning of of different type of symmetry, like CPT symmetry. Shall we take this question right now, or
What's the meaning of a different type of symmetry like CPT? So CPT is like it's that CP stands for CP violation, but T is time, which I remember. Um, but we don't achieve CPT symmetry. That's the point. That's the more interesting point, because um, what was important at some point is that whether parity is whether we have symmetry in parity or we have symmetry in time, but with time what we understood is that for the charge parity and the time reversal, we do not have all those three in a symmetry. And I am not sure whether any particular experiment is exploring that, because I mean it's I haven't not particularly worked on this particular topic yet.
no problem? Okay, Ritu Garg is asking this question. Hello, sir. How much is revealed about dark matter and dark energy?
So it's dark because we haven't really revealed anything. We just know that it exists. We have gravitational lensing. We know for sure that there is dark matter, but what it's made up of, what are the candidates, even we haven't proved that these, because there are 6 7 theoretical candidates for dark matter. LLP is one of those, but we haven't proved that or even proved that any of those are the exact candidate for dark matter. And even we haven't been able to detect any of those candidates, and that is why every general purpose experiment in high energy physics are now focusing on dark matter.
So, Ritu, you got your answer, and I also got the answer for my first question. So, this detection technique, like the way you explained beautifully, is that you are showering 1 billion electron or protons from here. Statistically, you're trying to understand. In case of a dark matter detection, also, what is the procedure? Are we going statistically, or we are trying to understand in terms of exact some kind of a detection from the space?
Yes. So no, here we don't. I mean, the that statistics is just related to whether we are able to collide some protons and create some proton collisions. But uh, beyond that point, whatever decay that collision generates, we try to capture all those. We have nothing to filter out. We want everything, every data. And then we try to find whether we have been able to look for an LLP. So for example, there is a particular reaction where Higgs decay into an LLP, which is a semi-leptonic decay. And for that, we would from all of the collision data, we would like to filter out those data where Higgs has decayed into LLP. So similarly, you would like to look for I mean, there are theoretical Feynman diagrams for what kind of decays can lead to LLPs, and you want to match those with whatever data you have collected. So you don't
Right.
have any control over the data, right?
Over the data, right?
Yeah.
Okay. So what you are saying, those data again, when they're collected, they are analyzed. So you need data analysts. In order to do that
Yes.
analysis, you need AI. So it is a sum total of everything: electronics,
Yes.
engineering, pure theoretical physics, AI,
Yes.
data
Yes.
analysis. It's a huge thing. Okay.
Yes. Yes. Yes.
So we have got Muhammad Hamza asking this question. Can you explain about coupling in cavities?
I'm not sure what does he mean by cavities. Yeah. You are muted, I think, Shonal.
Yeah, if
Yeah.
Mohammed can explain it better, I would. Okay, coming to
Yeah.
my next question is that suppose we detect dark energy. Suppose we detect. Now, my question to you is that once we detect the dark energy, what is its impact on our understanding of the universe expansion? I mean to say, what benefit it will give to us?
Mhm. So as you, it would give us the benefit of satisfaction, I would say, because as humans or as scientists, we are always curious. We always keep asking what more. After Higgs, we kept on asking what more, and now we sometimes try to use Higgs as a detecting Higgs as a probe for LLPs. And if we are able to detect LLPs, so we would know that because dark matter, because standard model doesn't assign any candidate for the dark sector, and if we can detect anything which is dark sector, that would be something beyond the standard model, and that would be the starting point of a new physics which is called beyond standard model physics.
Beyond standard model. And you are
Yeah.
working on that because your
Yes,
profile
yes,
talks about beyond standard model. We
yes,
are
yes.
coming close to the end. It is almost 50, 51 minutes. Uh, as in case of laboratory experiments, which CERN and other research laboratories are doing, can you tell us that what are the basic challenges that we are facing in order to directly or indirectly detect dark matter?
Basic challenges is mostly on the electronic side, but there are still, for example, there are still general purpose detectors which are working. Could you please share my slides once? Yeah. So like I said, that LHCb is a forward spectrometer. That means one beam of proton comes from here, one comes from here, and then all these red lines that you see over here, these are the scattered decays from the point of collision, and that is along the LHC beam. And but till now LHCb doesn't has any detector which is transverse to it. I mean, CODEX B isn't installed yet. Similarly, other experiments like CMS, Atlas, or even other experiments around the world, they don't have detectors which cover entire the entire phase for detection. What I mean is, yes, this. So uh, this is a very important diagram, I would say, because in the transverse direction we have codex p matushala, and in the forward region we have phaser at CERN, na62 at CERN, and lhcb at CERN. But the lhc coverage is atlas cms lhcb. What this is basically, that we try to cover as much as direction, from as much as directions as we can, so that we have scope of detecting uh, different masses of LLPs, uh, starting from lighter to heavier. These are the lighter LLPs, and these are made for detecting the heavier LLPs, as you know. Um, so that's the one main thing, that most of the experiments do not have any, the of the prior experiments, they do not have any dedicated LLP detector. And secondly, on the electronics point of view, is that most of the experiments lack proper or much more sensitive machine learning algorithms to detect even the slightest signature which is beyond standard model. So we are still exploring on the machine learning side, as well as on the electronic side as well. But you never know. Very recently we might find something.
Coming lastly to my question, Abhinav, if you can let us know in a very simple layman's language, first is that what is Monte Carlo simulation? And in terms of the computational power and algorithm, what are the advancements that are happening in order to, I would say, enhance the capabilities of Monte Carlo simulation?
So Monte Carlo simulations are, I mean, if I talk in the space of high energy physics, we try to simulate how a detector. So we have Giant 4. Gian4 is a high energy physics software uh, built by physicists, which has the entire geometry of the detector in it. And then we have Pythia, which is an event generation software, again built by us. And I mean, not me, but some other people. And Pythia generates the particle collisions, the data that the particle collisions might generate, and then those data are passed through Gian4 to replicate how the detector would react to that particular kind of collision that we generated using Pythia. So before implementing anything on the heavy machinery that you have in front of yourself, you first did everything on the computational base, and you have a relevant point of view to set your hardware in those particular constraints or in those particular parameters, so that you have the best output. Because each time you switch on the LHC beam, you are losing beam time, and you are losing time. I mean, uh, to run the experiment, it's costly to run the experiment. So you want to make sure that you have the best scope of detecting what you want to detect. So that's why, and on the AI side, is that most of these machine learning algorithms use boosted decision trees, or mostly like neural networks, CNNs, and artificial neural networks for searching of certain kind of high energy physics parameters inside the collisions. So, for example, in heavy ion collisions, what they'll try to look for is that if they have low centrality, they want to predict the centrality of the collisions. So when two nucleus is passing, so when two heavy ions are passing nearby, there are very, I mean, rare cases when they are colliding head on. Most of the times they are just they have just 10% overlap, or they have 40% overlap the nucleuses while colliding. So more they overlaps, more amount of data you can create from a particular collision. So these we try to predict that at what particular parameters, if we set the detector, we can actually have better centrality on heavy ion collisions. And there are other parameters for other experiments as well.
Okay. Mohammed Hamza is clarifying radio frequency cavities used to accelerate particles when I was asking coupling in them.
I'm
So
not
he,
sure.
yeah, yeah,
I'm not
yeah,
on the
absolutely,
accelerator side, so I might not be
absolutely.
able to answer this.
Okay, so Abhinav, a lot of thanks for coming today. So you have got your day scheduled, as I understand, although today is a Sunday.
Yeah.
Any kind of an advice, especially to the students aspiring, who we would like to give in order to move ahead, not only in CERN but as a whole in particle acceleration or in particle physics as a whole.
Yeah. I mean, in India, I know that when we study particle physics, we always just think of theory. I was myself in theory, and I would like to. I mean, I would like to appreciate if more and more people would try to make the theories that we study and into practicality. And for that, we need to invest more on the technological aspects of particle physics, and more on the coding aspects of particle physics. So I mean, if you would like to learn those and contribute towards these experiments, there is not just CERN, there is KEK in Japan, and there are other labs like Fermilab in the US. You can work on those and try to find a good summer internship, or maybe a good technical studentship somewhere where you can learn those, right?
Abhinav, my last question would be that if you can let us know that what are the future plans and upcoming projects at CERN and how they might, I would say, further push the boundaries of high energy physics research.
Yeah, so currently we are entering. If I may just have my slide for a minute, I have a very good picture for this. Currently, we have yeah, this one. We are in 2025, and if you can see my cursor, we have the higher luminosity LHC coming on in 2029. and for this we would have more, I mean we have thrice or four times more huge amount of data, and we are hoping to find more heavier particles and even LLPs in this era. And for that, we will be closing the LHC beam in 2020, in 2026, early 2026 we will be closing the LHC beam, and it is termed as long shutdown 3, and that is what my entire doctoral studies is over here, to upgrade the LHC and the experiments. And also there is a future experiment at CERN, which is FCC, that is the Future Circular Collider. It is supposed to be 100 kilometers in length, whereas our LHC is 27 kilometers. Also, the construction, or even the green flag for funding the FCC hasn't been there yet, but there has been simulation studies for FCC before giving any green flag to start building anything related. It's a very interesting thing.
How many Indians currently you have, your friends or anybody who are working at CERN? We have Indians working at CERN?
We have, I like, but most of them are at universities. They are LHC users. But I mean, I have met close to 40 Indians who have their offices at CERN, out of some 5,000 people who work at CERN. But it's a good
Right.
number from India.
It's a
Yeah,
good number, obviously.
yeah.
So when are you planning? When is the next visit at the LHC down the earth? I mean to say, right at the center.
Yeah. So this week I'll be going for visiting the LHCb because I'm working on the upgrade of LHCb. So we'll be installing something, and in the coming weeks, when the LHC won't be working, it would be shut down. It would be open to us, as well as I'm not sure on the authority side whether it is free to visit for the public. But from 2026, I think it's long shutdown. Entire year you can visit the
So
LHC
what is the
underground.
reason it is shutting down? Maintenance?
It's no, it's shutting down for an upgrade. We need more data. Yeah, that's why.
Okay, so please do send me also some of the LHC visit, photographs,
Absolutely,
which I'd like to
absolutely.
share on this channel so that viewers can also come to know.
Sure,
Although I saw few
sure.
of your pictures standing behind Nataraj today at LinkedIn, it's quite highly appreciable. So thank
Thanks.
you, Abhinav. Thank you very much, and please don't disconnect. I will just have a few words with you, and thank you very much for all the
Absolutely,
viewers joining. I hope Abhinav you enjoyed these questions. As I always say that
absolutely. Thank you.
the my subscribers are very intelligent, knowledgeable people who always motivate this kind of a podcast. So just stay tuned, Abhinav, and thank all the viewers for this wonderful. I think we have learned a lot regarding something very technical, yet something very beautiful, and what is the future prospect of CERN as well as particle physics. Rudrasi is saying thank you. So thank you,
Thanks,
Rudra, for
Rudra.
joining with us. Thank you very much. Just be.